Hello everyone and welcome to lesson 11 on the Save My STEM Physics channel. Today we will be talking about exchange particles or bosons and also about the weak interaction, which is, from fundamental forces, the last lesson, something felt between all particles which causes radioactive decay. So we'll be talking about specifically uh, beta decay, so beta minus and beta plus decay. So getting straight into the content then, what is beta minus decay and what is beta plus decay, and how do we know that they're right? Because particle physics is something which is very difficult to observe, so we employ something called conservation laws, which is probably going to be in the title of this video, even though it's not the title of the lesson. And conservation laws go all the way back to, if you let me flick back for a second, we have, do I not have this written down? Oh yes, here. QBLS, or cubules, as my physics teacher refers to them as, and I will probably call them cubules a few times, so please don't get tripped up on that, but QBLS, which stands for charge, baryon number, lepton number, and strangeness. And in the weak interaction, if you have particle A shoots out particle B plus C plus D, Q on the left hand side, sorry, equals Q on the right hand side, B equals B, L equals L, and if it's a weak interaction, strange might equal strange. It doesn't matter. It might be 0 to 0. It could be -1 to 0. It could be -1 to 2. It could really be anything. Um, uh, it doesn't matter. Strangeness doesn't have to be conserved in a weak interaction, but the rest of them do. In any other interaction, strangeness does have to be conserved, but in a weak interaction, it does not. So we'll get directly into it. Beta minus decay, the letter beta looks like that. Beta minus decay is when a neutron, denoted by the letter N, emits decays into a proton, because a proton is more stable than a neutron, something from the first lesson on particle physics. It emits an electron, which is electron minus, or it is referred to sometimes as a beta minus particle. They are the same particle, and also something else. But this is what you saw at GCSE. So where has the something else come from? Well, let's have a quick look at it. Q on this side is equal to 0, and the Q on this side is equal to 1 minus 1, so 1 from the proton minus 1 from the electron equals 0. So our charge is conserved. Our baryon number on the left-hand side is 1, since neutrons are baryons, and our baryon number on the right-hand side, sorry, did I just call that one the right-hand side? That one's the left-hand side. Our baryon number on the right-hand side is 1 from the proton plus 0 from the electron, because that's a lepton, not a baryon, which equals 1. So our baryon number is conserved as well. Our lepton number on this side is 0, and our lepton number on this side is 0 plus 1 equals 1. Wait a minute. 0 doesn't equal 1. So this interaction here doesn't exist. So how are we going to balance it out? Because we want these two numbers to stay the same. These are already fine. But we need to take away one lepton number. And we're going to do that by adding an an electron antineutrino. Because what that's going to do is it's going to change this to L equals 0 plus 1 minus 1. That has a negative 1 lepton number because it's anti, and that makes it 0. And phew, we're saved. Physics hasn't been broken. So that is beta minus decay, and that is how that works. The mass energy of the system is still the same, and our conservation laws have been achieved, so we can safely move on with beta minus. And now we're going to get onto beta plus, which is the same but opposite, as you can probably tell from the name. So beta plus is when it goes from proton to neutron plus positron, which is also referred to as a beta plus particle. Again, something you might have been able to predict. And we're going to employ our same ideas here. We're going to get Q equals 1, Q equals 0 plus 1 equals 1. So our charge is conserved. Baryon number equals, oh, sorry, you can't see this, sorry. Baryon number equals 1. Baryon number equals 1 plus 0 equals 1. Baryon number is conserved. Lepton number equals 0. Lepton equals 0 minus 1 equals minus 1. Wait a damn minute, the same thing's happened again. So all we're going to do is we're going to do the opposite of adding this, and we're just going to add an electron neutrino, because that's going to get rid of that. And instead we're going to get L equals 0 minus 1 plus 1, which is 0 again. And phew, physics hasn't been broken again. So these are beta minus and beta plus decay. You need to know these. These are expected to know, and you need to know where the neutrinos are coming from because of our conservation laws. And you also need to know the exchange particles, which we are about to get onto just now. So each of the four fundamental forces has one or multiple exchange particles. So if I just put force and then E particle, E standing for exchange. Now, exchange particles are bosons, but there are some exchange particles. Well, there's one exchange particle which is not a boson, and we'll get onto that in just a second. So the strong, weak, electromagnetic, and gravitational forces, our fundamental forces from the last lesson, each have one or multiple exchange particles, as I've already said. Strong has a neutral pion. Weak has a W plus, W minus, or Z neutral. I put a line through my Z's because when I'm working with the letter Z in mathematics, it can sometimes look like a letter 2. So I put the line through to denote that it's not a number 2. But that is a letter. That is a Z. So W plus, W minus, or Z neutral boson. I'll just put the extra word boson there for a second. Electromagnetic has a virtual photon, which is denoted with the letter gamma. That's kind of not a great gamma, but who cares? Examiners know. If you do a bad gamma, they won't care. And gravitational has gravitons. However, gravitons are purely theoretical. And judging by the current laws of physics, we will never be able to observe a graviton. That's physics far too complicated for me at this point. But gravitons are the exchange particle for gravity, and they are theoretical. We have not been able to observe them, and we don't think we're going to be able to observe them. Now, this is also something that you're expected to know. You need to be able to know these. Yeah, so how are you going to remember these, and how are you going to know when they're used? That's another lesson that we will get onto, but I will shortly introduce some of them. So, W plus is there in a beta plus. So plus and plus go together because beta plus is a weak interaction, so it's going to use a weak boson, which is a W boson, and if it's beta plus, it's weak plus, and if it's beta minus, it's weak minus. So W minus and W plus. And then Z neutral isn't actually seen in any A-level interactions, but it is there to sort of keep the weak force in check. The virtual photon, the way I remember it, the way I remember the photon part at least, is the fact that it's electromagnetic. The electromagnetic spectrum is the light spectrum, and light contains photons, which is where the photon is coming from. But also, the way to remember the letter is what is on the electromagnetic spectrum, gamma rays. So the letter is gamma. Now I don't know where the virtuals come from, but I just know that it's virtual, so I'm going to piece together the photon and the gamma by themselves. Gravitons obviously come into place when there's attraction between two particles with mass, and the strong exchange particle, the neutral pion, comes into place in any strong interaction, which we will define in a later lesson. One thing you may be questioning actually is, hold on a second, pions are not bosons, they are mesons, and you would be correct in saying that. I have that written here. Pi 0 equals meson. Again, this is another what the hell moment for physicists. But what the pion is doing is sort of taking the role of the exchange particle. So it is fulfilling the role of the exchange particle. It's making sure that the strong interaction has a particle which is carrying the force between the particles which feel the strong interaction, and therefore it is the exchange particle for the strong interaction. There is some more work on this coming in 2 lessons time, which will hopefully come soon under the lesson 12 Feynman diagrams, which contains a lot of very nice diagrams, which is a lesson I'm actually quite a fan of. So yeah, that concludes our lesson for today. Hopefully that all makes sense. And just remember to use your conservation laws to piece things together. The conservation laws don't just come into place for exchange particles. Hope this has helped. See you in the next one. Bye bye.